So we're going to continue with some more examples of graphing hyperbolas, and before I start a new example, I just wanted to go back to example 1. Here's our work from example 1, and make sure that everybody realized that the vertices for this hyperbola are at 3, 0, and negative 3, 0. I didn't actually label them as a vertex here and vertex there. Just want to make sure that's clear. Here's a vertex, and of course the foci are labeled, and also the asymptotes on that hyperbola. So that was example number 1. And also, before we start another example, I want to go back to these general forms of the equation. And now that we've worked through a problem, I think it's easier to look back at this form: x squared over a squared minus y squared over b squared equals 1, and the reverse, and talk about how you can kind of recognize right from the beginning whether you're going to have intercepts on the x-axis or the y-axis. If the x squared term is positive and y squared is negative in the original equation, we're going to end up with intercepts or vertices on the x-axis and not on the y. But if the y squared term is positive and the x squared is negative, then we get the reverse. That's the situation where we get intercepts on the y-axis and not on the x-axis. And so let's go ahead and start exercise 2. Oh, and before we start exercise 2, just below exercise 1 on the printed handout is a step-by-step procedure of what we're going through right here, written out in words. It's between exercise 1 and exercise 2 on the handout. So if you want a summary of this process, take a look at that. Plot the intercepts, draw the central rectangle, asymptotes, draw the branches and the foci. That kind of breaks down the process that we're going through right here. So exercise 2 on that handout, I've written out here in a separate sheet. We're going to graph this equation, 25y squared minus 4 x squared equals 100. And now that is not written in standard form. When you first glance at it, it looks a little bit different from those fractions we've been seeing with the 1 on the right-hand side. Now, if you want, you can go ahead and start trying to find intercepts just from this form. You don't need the standard form to find x or y intercepts. But I think for this one, I'm going to go ahead and try to put it in standard form. Let's see if we can do that. And I just want you to be aware that if that seems too complicated or too messy, it's okay right at this point to set x equal to 0, solve for y, set y equal to 0, solve for x, look for those intercepts. But here I'm going to try to write this in standard form. Now, to get standard form, I want a 1 on the right-hand side. So I'm going to divide both sides by 100. Take 25y squared minus 4x squared, divide by 100. That's going to equal 100 divided by 100 on the right. And the left-hand side I can take apart as 2 separate fractions. Equals 100 over 100. It's going to be equal to 1 when I reduce. And I can reduce my 25y squared over 100. I can divide by 5 and 5 above and below. And that's going to reduce to y squared over 4. 25 goes into 100 4 times. Minus, I can also reduce the right-hand side. The 4 is going to cancel out. If I divide by 4 above and below, I get x squared over 25 equals 1. So there, it wasn't too hard to put that equation into standard form. And now, again, if you learn to recognize the way this equation looks, because the y squared term has positive coefficient, you should suspect that I have y-intercepts and not x-intercepts. Now I'm gonna approach this naively, and I'm gonna pretend like I don't know. So if I'm looking for x-intercepts, I would set y equal to 0. And if I set y equal to 0 in that equation, 0 squared over 4 minus x squared over 25 equals 1. So I get minus x squared over 25 equals 1. Minus x squared is 25, but that means x squared is negative 25 if I multiply both sides by negative 1. So I would try to take square roots of negative 25, which has no real solution. And so there are no x-intercepts. On the graph of this hyperbola. You do not have to write out those steps if you learn to recognize that there are going to be no x-intercepts just from the equation, right? Because we know that minus sign is in front of the x squared. If I look for y-intercepts by setting x equal to 0, y squared over 4 minus 0 squared over 25 equals 1. So now, again, I get a nice positive situation here with y squared over 4 equals 1, y squared equals 4, y equals plus or minus square root of 4, so y is plus or minus 2, 0, 2, 0, negative 2 are my y-intercepts. And these are going to be the vertices, what we call the vertices of the hyperbola that we're looking for here. Okay, and now in order to start with my graph, though, I need those co-vertices. I need those conjugate vertices. So if I take the equation in standard form, and if I change the order of the subtraction, this is called the conjugate hyperbola. And its vertices are going to be helpful for drawing that central rectangle. And we need the central rectangle to be able to draw the asymptotes. Now, the vertices here on the conjugate hyperbola, I think you can see, are going to be the same as what would have happened back on the original hyperbola if we had a positive 25 instead of a negative 25. So if you can see that idea, you don't have to write out all the steps. But if I set y equal to 0 to look for x-intercepts, I'm going to get x squared over 25 equals 1. Here I get x squared equals 25. And so x is equal to plus or minus 5. Here I'm able to take the square roots because for this conjugate hyperbola, I end up taking a square root of positive 25. So these are x coordinates, so 5, 0, negative 5, 0 are the co-vertices, or I actually prefer to call them the conjugate vertices. And by the way, if you accidentally tried to set x equals 0 to find y-intercepts, do you see that for this equation, you're going to get no solution for the conjugate hyperbola? Because we've just turned the situation around. If I try to set x, x equals 0 in the conjugate hyperbola equation here, down here, then I'm going to have y squared equals a negative. So just the reverse of what we got in our original equation. That's for the conjugate hyperbola. So the conjugate hyperbola will have just two intercepts on the opposite axis that the original hyperbola has intercepts on. Right, so now we're ready to start drawing our graph. And let's see, I have to plot my intercepts and my conjugate intercepts. So I'll make this x, this y. So my actual intercepts, my vertices, are at 0, 2, and 0, negative 2. So I'm just going to 1, 2, negative 1, negative 2. And my conjugate vertices, which are not actually points on the hyperbola, are going to be at 5, 5, 0. Sorry, I pushed that up too far. And negative 5, 0. Put a little mark there. A little mark there. And the point of having these conjugate vertices. Now, here they're on the x-axis, right? While my regular vertices are on the y. And drawing these horizontal lines and vertical lines through the vertices and conjugate vertices gives me my central rectangle. And the central rectangle is what I can use to draw the asymptotes from corner to corner. X. And so for this example, because my actual vertices are on the y-axis, I'm going to have a hyperbola that has a piece above, kind of approaching those asymptotes, and it's going to have a piece, another branch below. And so maybe just to emphasize 0, 2, 0, negative 2. Those are my two vertices. Vertex. And here's a vertex. And now we need to find the foci and the equations of the asymptotes. To find the foci, we use our a squared plus b squared equals c squared equation. And because we're adding a squared and b squared, it doesn't matter which one of these goes first. I'm trying to get our standard form of the equation back up here. So the a squared and the b squared are the denominators in the standard form. A is actually 2, a squared is 4, and b is actually 5, b squared is 25. So I have to add 4 plus 25 to get c squared. 29 is c squared. So plus or minus the square root of 29 is going to be my c. Those are my coordinates, part of the coordinates of the foci. Now, where are the foci going to be? Are they on the x-axis or the y-axis? Well, because the intercepts of my hyperbola are on the y-axis, the foci are also going to be on the y-axis, right? The curve is wrapping around the foci above and below. So these are y-coordinates. And it helps to have a decimal, which is what, about 5.4. So this is approximately 0, 5.4, 0, negative 5.4. So 0, 1, 2, 3, 4, 5.4 is way the heck up here, right? And 2, 3, 4, 5, 6. So negative 5.4 is about down here. So there's a focus and a focus. And now the only other thing we need here are the equations of the asymptotes, right? The equations of the asymptotes. And they're always going to be in the form just y equals mx. The b is always 0. The y-intercept is 0. And you can just figure out the slope using a couple points on either one. The easiest is this upper right-hand corner, because this is 5, 2, x is 5, y is 2. I'm also going to use 0, 0. So to find the slope of 1, I'm going to use 0, 0, and 5, 2. And so that slope is going to be 2 minus 0 over 5 minus 0, or 2/5. So y equals 2/5 x is one of the asymptotes. The slope of the other, you can always just memorize this if you want. Just use the negative of 2/5. It'll be y equals negative 2/5 x. That they always are going to turn out in this way. If you weren't sure, you could just pick a point on the other asymptote, like 5, negative 2, and you could compute the slope of the other using 5, negative 2, and 0, 0. So that's going to have negative 2 minus 0 over 5 minus 0 is negative 2/5. But again, you don't have to go through that calculation each time. You can just take the opposite slope of the first slope you calculated, because it's always going to come out this way. The other asymptote has equation y equals negative 2/5. So here we have y equals 2/5 x is that line. My other asymptote is y equals negative 2/5 x. And I want to darken my hyperbola here because you barely see the hyperbola in all this drawing. The actual hyperbola is this kind of stretched out, overturned U shape, and U shape up above, again stretched out because of the way the asymptotes are. Okay, there we go. We got a little bit more. And I think I want to try to get our equation in there. The original problem was up above, and then we put that equation in standard form to be able to draw the hyperbola that you see. Okay, and then just one last comment about this guy. We we don't draw it, we talk about it, but we didn't draw it. I've talked about this conjugate hyperbola, you know, that equation we got when we turn the subtraction around. Again, we don't want to add it to this picture, but that conjugate hyperbola would be here and here. So there's a kind of a twin or a pair. That's not really part of the graph we want here, but just that's the meaning of what this conjugate hyperbola is that we talk about. When you change the order of subtraction in the equation, if we were to graph that other hyperbola, we'd be getting something that I've kind of outlined very lightly in red there, side to side. So we don't need it here. We just need the blue. And we're going to do a couple more exercises and then in another video, and then we'll be through with this section.